Afternoon, everyone. CSIR-NEERI welcomes the 8th day of webinar lecture series on advanced water and wastewater treatment. Today we have a well-known person, Professor Emmanuel Mousset, with us. He is from France, and we have a good relation between from 2016 onwards through Professor Oturan. He was working under Professor Oturan in the field of electrofendon. Then for the panels, we have Dr. Anand Singh from NIT Calicut, Dr. Ambika S from IIT Hyderabad. I think Professor Manu will join from NIT Surathkal soon. So last a few days, we discussed about advanced oxidation process and its applications, everything. So today, in all the advanced oxidation process, we have one oxidizing agent, that is hydroxyl radicals. So today we will discuss mainly on the activities, what are the main reactions mechanisms of hydroxyl radicals for the oxidation of all these organic pollutants. So Mousset will explain how the hydroxyl radical will degrade all the organic pollutants present in the water. So before starting the program, I will just introduce Professor Mousset. Professor Mousset, after getting an Erasmus PhD from Joint Doctorate Program, University of Paris-Est, France, University of Casino and Southern Lazio, Italy, UNESCO IHE from Netherlands in 2013, Dr. Mousset pursued as postdoc successfully in National University of Singapore, NUS, and in Helmholtz Center for Environmental Research, UFZ, Germany. He obtained a tenure position in 2016 at the French National Center for Scientific Research, CNRS, as senior scientist. He focuses his research work on advanced oxidation or reduction processes, especially with electrochemical processes for environmental protection, including for water treatment and reuse. He is currently implementing his research topic through collaborative project with French laboratory, that is Institute European des Membranes, IEM, from Montpellier, as well as with University of Nankai from China, University of Notre Dame, USA, and University of Qadiayat, Morocco. In parallel, he teaches electrochemical engineering to MSc students in ENSIC Engineering School of Nancy, France. He published several tons of research papers in the distinguished international peer-reviewed journals of the area, along with 4 patents deposited. He has been invited in 10 major international conferences in his area of research. He is the guest editor for a special issue in Electrochemical Acta journal. He has been awarded the International ISE Elsevier Prize for Green Electrochemistry 2018. Professor Mousset, please.
Well, thank you, Nidesh, for this introduction. Now I'm sharing my screen and my presentation. Okay. So as Professor Nidesh said, so I'm a CNRS researcher in the Reaction Chemical Engineering Laboratory, and I'm working especially on electrochemical application for water treatment. And I will present you today the hydroxyl radicals reactivities, their applications for water pollutants. First, just a brief definition of advanced oxidation processes. I'm sure that you have seen that maybe already during this lecture series on advanced oxidation processes, but I still wanted to start with that just to because it will influence both there is a link between the reactivity and the definition of advanced oxidation processes, because it consists of near ambient temperature and pressure water treatment processes, which involves the generation of very powerful oxidizing agents. Okay, and such as hydroxyl radicals, which radicals in solution in sufficient quantity to effective water purification, which was defined by Claes et al. In 1987. And what is important is to remind that it's under ambient temperature and pressure, and its powerful oxidation oxidizing agent involvement, and it's in solution and in sufficient quantity. And hydroxyl radical, thanks to its properties and reactivity, we can deal with this. We can correspond to these definitions, and this is what I will show now. So just a brief reminder about oxidoreductions theory. Very simple reminder. Oxidation reactions. So you give an electron from reductor to oxidant, and then you have one or several electrons. For reduction reaction, you consume an electron or several electrons. An oxidant consume an electron to give a reductant. And you can use gamma rules to check the thermodynamically favorable reaction. Here you see the axis, vertical axis that represents standard potentials in volt versus standard hydrogen electrode. And the left is oxidant species, and the right is reductant species. And here is one oxidoreduction couple, OX1, red one. And here is another oxidoreduction couple, OX2, red 2, and with a lower standard potential. And following the gamma rules, you can do a gamma here, right? So oxidant 1 react with red 1 to give oxidant 2 and red 2, which is equivalent to the global equation here, OX1 plus red 2, that give oxidant 2 plus red 1. So this is okay, simple theory that everybody knows now. But so I introduce that just to show you then the table of several oxidizing agents with different standard potential. And that starts from here, from chlorine dioxide, ClO2, chlorine, Cl2, so their standard potential 1.27, chlorine 1.36, hydrogen peroxide H2O2 around 1.76, persulfate S2O8 to minus 2.01, ozone 2.07, ferrate iron FeO4 to minus 2.2, sulfate radical iron anion SO4 minus 2.6, hydroxyl radicals 2.8, and fluorine F2 to 3.06. And according to the gamma rules, I think the standard potentials, when the standard potential is increasing, their oxidation power of these couples is increasing. And so we can see that hydroxyl radical is second after fluorine, okay, regarding the standard potential. So its oxidation power is very high compared to other compounds that you can find here in this table. And I added these compounds because they are famous for ozone for water treatment, especially ozone is used. Persulfate now is being used. Hydrogen peroxide, chlorine, and chlorine dioxide for disinfection is used as well. But we can see that hydroxyl radicals, what is interesting is that their standard potential is much higher. That is still second after fluorine. So why we don't use fluorine for water treatment? But that's obvious, because fluorine can be a pollutant for water, and this is something that we need to remove in water. So we don't use fluorine for water treatment application, even though the standard potential is higher. So hydroxyl radicals appear to be interesting. Due to its oxidation power regarding the thermodynamic point of view. But then, so we see that thermodynamically favorable reactions between OH radical and most of the compounds could be favorable, yes, because thanks to the high standard potentials. But what about the kinetics? Is it very fast, slow, or very slow reactions? Because even if it's thermodynamically favorable, the kinetics could be very slow, so then it's useless. So then the kinetics has to be studied as well. We'll start with the Lewis structure of hydroxyl radical action, and so it's constituted of an oxygen atom and hydrogen atom. Okay, there are bonds between them, and the oxygen atom have an unpaired electron, which make it a radical species, and that also make it a very electrophilic species, and also therefore very reactive species. And also, since it's very reactive, it has a very short lifetime. It's in nanoseconds range. And yes, because it reacts very quickly with the compounds around it. Regarding the mechanism of hydroxyl radicals action, so and up to date until 2 or 3 years ago, I will explain why later. We were mentioning always 3 main mechanisms of hydroxyl radical action. Dehydrogenation, which consists of hydrogen atom abstraction. So, for example, R is an organic compound, H is a hydrogen atom bound on the organic compound, and it gives then a carbon radical plus H2O, yes. An example here with phenol compound, we have an hydrogen, we have a carbon radical formation, okay, so, because hydrogen atom has been removed from the structure. We have also hydroxylation, which consists of an electrophilic addition and an unsaturated bond, which is particularly interesting in water treatment application, because many of the pollutants, biorecalcitrant pollutants in water, are constituted of unsaturated bond, especially aromatic compounds. Yes, as you can see here, A is aromatic, and hydrogen atom is bonded on this aromatic side ring, and then it produces aromatic HOH radicals that is bound onto the molecule, and then with oxygen it's become an aromatic hydroxylated aromatic compound, and then we produce also HO2 point and HO2 dot. Okay, so this is an hydroxylation, because you can see here that an OH function has been incorporated onto the aromatic cycle ring. Okay, so then we have also redox reactions, which consist of electron transfer. So this is reactions that we have seen, I've showed you about initially on this presentation about the redox reaction, oxidoreduction reaction. So a general way is an A compounds with having N balance reacting with hydroxyl radicals give A power N plus 1 plus OH minus. An example with iron, ferrous iron, Fe2 plus, that when it reacts with OH radicals, it gives Fe3 plus OH minus. Actually, I put this equation because in Fenton-based processes, it's a famous parallel reactions, famous waste reactions, because it consumed Fe2 plus, which is a Fenton reagent, and we don't want it to react with OH radicals. And it has been shown that it's one of the main waste reaction in Fenton-based processes. Okay. So basically, we say that OH radicals has no selectivity towards compounds for its reactions. Actually, it's not completely. It's not completely the case. There are some compounds in which it could not be reacts, but there are some compounds until 2018 we were saying OH radical could not react with them, and it's per halogenated carbon compounds like CCl4, C2CL6, etc. Because these compounds have no unsaturated bond, a carbon-carbon unsaturated bond, especially no hydrogen atom, and very high oxidation state. So how could we oxidize more these compounds since they have already a high oxidation state? So up to date until 2018, we were thinking that OH radical could not react with these compounds. I will just detail a bit more this part of reactivity of OH radicals, because it's part of a recent work that I published with Professor Turan and in 2018 in Applied Catalysis B. And so just to introduce until before articles were proposing ways of degradation of per-halogeno-carbon compounds through different way, according to literature, existing literature at that time. So with CCl4 that has been widely studied to check the reactivity of some radical and oxidant species or reductant species. And so heterogeneous photocatalysis process has been tried to degrade CCl4 in the presence of surfactant as organic precursor. And the hypothesis of mechanism was a complex formation between the surfactant functional groups and TiO2 surface responsible for the weak visible light absorption and the subsequent photo-induced electron transfer to CCl4. So in fact, they succeed to degrade CCl4, but they were assuming that it was becoming from the electron from a visible light activity reaction center to give CCl3 radicals and Cl minus, and then the CCl3 radicals, when reacting with oxygen, was composing CCl3OO radical, and then after mineralization, CO2 and 3Cl minus. So in this hypothesis of mechanism, OH radical was not finally involved in the reaction mechanism, though we know that heterogeneous photocatalysis produce hydroxyl radicals, but they were assuming that it was another species. Another work were working again with CCl4. They were applying methanol as a precursor in H2O2 photolysis. Okay, and the hypothesis of mechanism is that they were assuming that the methanol as precursor was reacting with OH radical to form CH2OH radicals, and then react with CCl4. Okay, so it's indirect oxidation, right? You start with a precursor, then you produce a species that will react with the species we want to degrade. Okay, and the reaction proposes that when you do H2O2 photolysis, so with UVC at 254 nanometer, you produce 2 OH radical that then react with a methanol, okay, and then you produce a radical, and this radical that is responsible for the CCl4 degradation to produce CCl3 radical. Okay, so again here in OH radical was finally not directly involved in the degradation mechanism of CCl4 of the per-halogeno-carbon compound. Another study was trying to degrade CCl4 with sonication. So it is well known that sonications decompose water molecules into hydrogen radicals, H dot, and OH radicals, and then CCl4 reacts with the hydrogen radical. And so the reaction proposed for CCl4 degradation is that H2O plus sonication give, as I said, hydrogen radical and hydroxyl radicals, and then the CCl4 react with the hydrogen radicals to give HCl and CCl3 radical. Okay, so you can see also that CCl3 radicals is always main byproducts that is proposed in the reaction pathway of CCl4. So again, here OH radical was not finally involved in the degradation mechanism, and hydrogen radicals was proposed in this mechanism. Another three other studies proposed CCl4 degradation with a Fenton-like process in aprotic solvents such as dimethyl sulfoxide and dimethylformamide as organic precursor. The hypothesis of mechanism was that superoxide ion O2 dot minus, which is a weak nucleophile and a reductant, was responsible for the decomposition of CCl4. And the reaction proposed was that CCl4 react with five molecule of superoxide ion and with water to produce HOCOO radical, anion radical, and then Cl minus production. Okay, but here again, OH radicals was finally not involved in the degradation mechanism, though that OH radical could be produced during the Fenton process. And what about the advanced oxidation processes condition in ultra pure water? Because in all these studies, they were adding a precursor, an organic precursor, and they never tried with only ultra pure water. And the thing is that with the pKa of HO2 radical oxygen superoxide ion is 4.8, and the pH in Fenton process is around 3. So in the previous studies based on Fenton processes, the HO2 radical was predominating, and it's a weak oxygen oxidant, and with a standard potential of 1.65 volts versus the standard hydrogen electrode. So the role of superoxide ion could be reconsidered. Okay, and this is what we have. So this was the introduction of our paper on this. And then we tried to show, we tried to do experiments with electrochemical advanced oxidation processes using different anode electrodes, okay? And so we tried first to check the electroactivity of CCl4 to see if there could be direct electron exchange, okay, with the electrode, so electron transfer reaction. And with PT platinum working electrode, we see that there were no peaks, so there were no direct, no electroactivity of CCl4, okay. And with classic carbon working electrodes, we could see that around -1 volt, there were a peak, and that could be attributed to the H2O2 electrode generation as a cathode, because it's famous to have H2O2 electrode generation as a carbon cathode. Okay, so in the presence of oxygen in the solution. And when we tried, so then we said, okay, so if we have H2O2 in the solution, could we have a degradation of CCl4? We did that, and there were no degradation of CCl4. So because H2O2 is a too weak oxidant for CCl4 oxidation, okay, degradation. So because there were no Cl minus released, and the TOC also remained constant, okay? TOC remained constant all along the experiment, and Cl minus were 0. And then with the influence of electron materials, we could say that the chloride concentration evolution from in solution could increase, because initially, of course, it was 0 because it's CCl4, but then it's quickly produced Cl minus with a different electrode, with BDD, which is boron-doped diamond electrodes that have a very high oxidation power that allows producing hydroxyl radicals at its surface. And with electrofenton with platinum, we could see also the production of Cl minus from CCl4 degradation. And so in electrophenton also we produce hydroxyl radical. Okay, and we did also a control, and there were no production of Cl minus. Okay. Okay, so what I wanted to say is that so there were serial managed generation, so there is degradation of CCl4 with burned up diamond. There is a fast degradation at the beginning, then it's decreasing again, and this is because of the conversion of Cl into chlorate and perchlorate, ClO3 minus and ClO4 minus, which is well-known reactions of Cl minus into chlorate and perchlorate with BDD at a certain current density, and we were in these conditions to produce chlorate and perchlorate. Okay, and with platinum in electrophenton systems, the degradation we could see also degradation and accumulation of Cl minus, and only OH radical was produced in this system. So the role of superoxide ion could be reconsidered in the CCl4 degradation and mineralization. If you look at the mineralization with total organic carbon decay and the respective rate constant, decay rate constant, so we could see that mineralization of CCl4 could occur, okay, and we could see higher mineralization yield with burned up diamond experiments. This is because we have a higher production of hydroxyl radicals in this case. Okay, based on that, we could define a pathway of CCl4 oxidation by hydroxyl radicals. We named that reaction ipso substitution to pair halogeno-carbon compound. And so the OH radicals is going on the carbon atom, okay, because there is a dipole, and thanks to this dipole, the carbon is positive, and then the OH radicals is attracted to this, and then the Cl minus of the CCl4 is ejected. So then we have the CCl3 OH, okay, and we produce a Cl radical, and then we have the CClO, okay, and finally we have a mineralization is to CO2, and then we could add a fourth action mode of OH radicals. So as I said at the beginning, there is hydroxylation, dehydrogenation, okay. We have electron transfer, and the fourth one, the ipso substitutions. And this is interesting, okay, because it enlarges the application range of advanced oxidation processes that all rely on the production of hydroxyl radicals and its reaction and reactivity. And for example, there are emerging contaminants like PFOA, PFOS, like perfluorooctanoic acid, that we found into the environment. And there are many studies we can start to see many studies on it in research area in order to try to degrade these compounds. And actually AOP are efficient to degrade this, and one of the mechanisms responsible for this degradation could be this ipso substitution, okay, that we can give for that. So now regard the kinetics, we have seen before the mechanisms of hydroxyl radical action. Now we are looking at the kinetics of hydroxyl radical actions with organic compounds, and the general reactions that react with organic compounds, organic reagent to produce organic products. Wrote here OH radical plus R that give P. And usually a second order kinetic is considered as first approach, which is written here, minus differential of air concentration is equal to the absolute rate constant, second order rate constant in liter per mole per second, times OH radicals times the concentration of the region of the organic compound to degrade. Okay, but usually the rate of hydroxyl radicals concentration is considered constant because it's quickly produced and quickly consumed as a radical species, because it's very reactive. As I said at the beginning, it's nanosecond lifetime. So we can say that the variation of concentration with time is constant of hydroxyl radicals, which calls that, and we call that a quasi-steady state approximation. And then the rate law can be assimilated to a pseudo first order kinetic. So we have the K apps times OH radical concentration, which is equal to the apparent rate constant, K app. And then we can replace that in the equation, and K apps times the concentration of the compound to degrade. Okay. Be careful, because it's not always simple global first or second order. It can be much more complicated according to the solution. If you have only radical with one compound in solution, that can be okay. But then if you have matrix inside, like other compounds that could react also with OH radicals, if you have other in real effluent, you can have some inhibitor or competitor, as I will show after. Then you can have different kinetics law. Okay. So the pseudo first order is usually considered in second minus or -1 or minute -1. And in this case, to determine this rate constant, when we assume a pseudo first order, there is an exponential decrease. So you can already, by seeing your curve, that represents the concentration of the compound to degrade versus the time. Okay, the treatment time. You can see that visually that it should be an exponential decrease, and with this reaction, the concentration of the compound to degrade is equal to the initial concentration times exponential minus K app times time. And to determine the K app, we take the logarithm of the initial concentration versus the concentration of the compound with time, that is equal to the K app times T. And then when we plot the logarithm versus time, you can have a linear plot. Okay, and then the slope of the curve gives a K app value. And then with this K app, usually we also determine the half-life time of the compound, which is in second or minute, which is equal to the logarithm of 2 divided by the apparent rate constant. Okay, so this is a way to determine these constants. Some range of constant orders with different kind of compounds. So here on this slide, I show you the reactivity of OH radicals with alcohols, alkanes, carboxylic acids. So for example, oxalic acid with this kind of formula, acetic acid, dichromethane, formic acid, bromodichloromethane, dichloroacetonitrine. And the range of kinetic rate constant with this kind of compound, alcohol, alkane, and carboxylic acids, is in the range of 10 power 6 to 10 power 8 liter mole -1, second -1. And here are some examples. And with oxalic acid, the reactivity is the lowest compared to the other compound here. With formic acid, the reactivity is higher, the highest here, in 10 power 8 range. Okay, and with the other, it's in 10 power 7 range with acetic acid, for example, and the other one. So the other one here. Okay. And what is interesting in the water treatment application is that with cyclic aromatic compounds with containing unsaturated bonds, the range of kinetic rate constants are higher. It's 10 power 8 to 10 power 10 liter mole -1 second -1. As I said at the beginning, is that many of pollutants in water, organic pollutants in water, contain unsaturated bond and are cyclic or aromatic compounds. And here you have some example with lindane, diethyl phthalate. So there are some pesticides. Microcystin LR is algae that we find. That it's a toxin, mycotoxin delivered by some algae, cyanobacteria, that we try to remove when we treat the water if we have cyanobacteria. Sulfachloropyridazine, some pharmaceuticals, butylated hydroxyl, and RDX, which is used for explosive. Okay, and here you have some range of second order kinetic rate constants with these different compounds. And you can see that the range is 10 power 9 for all of these. And yeah, so it's higher than this previous one here, alcohol, alkane, and carboxylic acids. It was still here, it's still high, right? But so it can still react with them, hydroxyl radical, so it can be still be useful, but it's even more useful with this kind of compound. So it's an interesting feature, because more complex structures tend to be not biodegraded, but degraded more easily by hydroxyl radical. Okay. So regarding the influence of pH, so usually we have quicker kinetics with OH radicals and pronated form of the acido-basic organic compounds to be degraded. Okay, and then we have more efficiency at circumneutral and alkaline pH, but be careful not at too high pH, because the pKa of OH radicals and oxygen radical is around 11.9. So then if you have too high pH, you will have mainly oxygen radical, and you will have almost no hydroxyl radicals. So then the reactivity is much reduced. Okay, and also it depends the process that you want to apply, because if you apply Fenton process, for example, its optimum degradation efficiency is at around pH 3, because the iron that constituted the reagent, one of the reagents of the Fenton reaction, is soluble only at low pH, and then otherwise it's precipitates. So you need to consider not only the reactivity of OH radicals in this case, but also the reactivity of the other compounds that are inside the solution. So the influence of temperature, so of course you know the Arrhenius law, and so basically the kinetic rate constant increase with the temperature, okay? And you can, by drawing the logarithm of the constant, the rate constant versus temperature -1, power -1, you can have a linear trend, then you can determine the activation energy. But again, be careful with this trend of increase of reaction rates, because it depends also on the stability of the compounds and the reagents at the applied temperature we have, because even though the rate constant could be higher, then there are some species that are not stable at too high temperature. For example, hydrogen peroxide in Fenton reaction is not stable at temperature higher than 40 degrees. So then the reactivity is lower, even though OH radicals reactivity could not be impacted. But then the production of OH radical is much reduced at high temperature if you use Fenton reaction. The influence of matrices. The kinetics of degradation mineralization of organic pollutants generally decrease with real matrices because there is especially high reactivity with bicarbonate, sulfate, and chlorine. Okay, with that are competitor and inhibitor and react very easily with rich radical. Okay, so that's why it's important to perform the process in real with real matrices before saying that it's efficient. And there are examples of main interaction between compounds I and rich radicals. With nitrates, we have the rate constant given here. So it's 10 power 10, so it's very high reactivity. And then the reactivity decrease with this compounds. So with bromure ion, it's around 10 power 9. With carbonates, 10 power 8. With ammonia, 10 power 7. With bicarbonate, 10 power 6. And with dissolved organic carbon, it depends to the matrices. And there have been average downs on 10 secondary effluents from wastewater treatment plants. And the constant given were 10.1, 10 power 4 milligram of carbon per liter -1, second -1 of constants. So the activity is still quite high. Okay. And so it's important to take into account the kinetics of reaction of the rich radical inhibitor that constitute parallel reaction and in some way unwanted reactions. And the global kinetics of the oxidation of the targeted compounds. So K inhibitor in second -1. So for the pseudo first order, it's the sum of the constant times compound inhibitor concentration. Okay, and that needs to be deduced from the global kinetics. And I will have almost done with these last two slides with the application of hydroxyl radicals for elimination. So there are two main, I would say, applications. Is elimination for water treatment, the elimination of hard chemical oxygen demand. So the chemical oxygen demand that is not biodegradable and that contain micro or pollution or macro pollution, micro pollution. So at high concentration, especially in industrial effluent, or at very low concentration, especially at the outlet of wastewater treatment plants. So basically, biorecalcitrant organic compounds react with rich radicals, and then you have degradations that form byproducts, especially organic byproducts. And then if you pursue the treatment, you have a mineralization and a complete mineralization that produce CO2, H2O, and inorganic ions. That's to be reminded. And it means also that you need to be careful and to identify and quantify these compounds and check whether it could impair toxicity, biodegradability of the effluent, and then you need to manage it if so. Okay, so that's important. And here I gave some example of treated effluents that can be treated with process that involve rich radicals like textile effluents, pharmaceutical, pesticides, paper mill, industry, petrochemical, and landfill leachate, olive mill, cork boiling, tannery, surfactants, phenolic, reverse osmosis membrane concentrate. Okay. And the second application is disinfection. So inactivation of microorganisms like bacteria, viruses, protozoans. And we can determine the kinetics with using Chick-Watson law, famous law in disinfection area. And N0 and N are the number of microorganisms initially present and present after certain inactivation time T respectively. K is a kinetic rate constant of the microorganism inactivation, expressed in liter per milligram per second or in liter per milligram per minute. C is a disinfectant concentration, often given in milligram per liter, and T is an inactivation time with a disinfectant, often in second or minute. So we have the CT concept that in which the value of CT often given to quantify the disinfection, and this CT product is given in milligram per liter. But you need to be careful because there could be an initial latence phase without inactivation, and this CT value has to be deduced from the global CT for a given number of activation log. Okay, so I will finish here. Thank you for your attention.
Okay, thank you, Emmanuel Mousset, for this wonderful talk. So, Dr. Mousset, please stop sharing your slide so that we can have a formal discussion.
Okay.
Okay, thank you. So we can go for a panel discussion now. Dr. Ambika, please raise your question if you have.
Yeah. So my question is application of this advanced oxidation process in practical conditions, especially focusing on groundwater pollution and remediation. So what's your opinion on that? How much it can be like possible to use advanced oxidation process for remediating the groundwater pollution, maybe organic or inorganic pollution?
Yes, so yes, because when you were mentioning me the groundwater pollution, I was thinking yes, especially for inorganic compounds, and here representing mainly oxidation of rice radicals with organic compounds. So with inorganic, so you will not, I mean, you cannot degrade inorganic, right? So you only change the oxidation state. So what is possible is to change the oxidation state of some compounds in order to either make it insoluble, so then you can use precipitation, or you change the oxidation state like Chrome 6 to Chrome 3, that is famous reaction, in order to reduce drastically the toxicity of the solution of the effluent. So you can use advanced oxidation processes involving oxidation with hydroxyl radicals for inorganic compounds. It's not the main area, but it can be done. Okay, and you need to compare the efficiency with other kind of processes that could be used in parallel. And for organic ones, if you have some organics like some pesticides in the groundwater, yeah, you can use with pesticide for sure. Even if they have already a high oxidation state like organochlorinated compound, organohalogenated compounds, they have already a high oxidation state. So you can reduce this compound, but you can also oxidize them with hydroxyl radicals. It's possible.
Okay, thank you. My next question is on the catalyst which we have used for producing these radicals. These radicals, most of the times, it has to be kind of generated from a source material. So what's your opinion on that source material and zinc? Because always we need to go for a secondary material. For example, iron pentons reaction, we need to have iron. For electrolysis process, we need to have electrode material. Externally, we need to supply few other things. So what is your view on this, producing these radicals and quantifying the radicals? Because most of the time we have to have the quantification of radicals, then we can have the idea of the amount of pollution removal. So in this case, it mostly depends on the catalyst and a few other environmental conditions that only influences this radical production. So what is your comment on that?
Yes, so I didn't show about the quantification of hydroxyl radicals. The thing that, yeah, it's interesting to know the amount of oxidants we produce in order then to define the dose to apply for the treatment. That's for sure, that's interesting. So this is what we can do easily with ozone process with some reactive oxidants that are not too reactive to be easily quantified. And then it's easier to size the process. But with hydroxyl radicals, it's a bit more complicated because it's very reactive. So its quantification can be done with indirect method usually, or ESR, ESR techniques as well. and in this case you can quantify it, and then you need, so if I understand well your question, so the first thing is to quantify where the hydroxyl radicals amounts, yes, to be produced in order to size better the reactor. And then you have different kind of advanced oxidation processes that involve core reagents like iron and H2O2 in Fenton process. In UV photocatalysis, you need to have a photocatalyst, and so then this consideration needs to be taken into account in the cost efficiency and in the green approach as well. And so when you use catalyst, you need to be careful to don't release it if it's coated on the materials and some stuff like this. And then for Fenton, for example, since you need to be at pH 3, it can be a problem because you need to acidify the refrigerant and then you need to neutralize again. So that's why there are many work and now on the Fenton on the neutral Fenton system. Okay, that could allow to operate at neutral pH. But then again, you could release some argon when you do that. So you need to be careful with that. Okay.
Okay, thank you, Mr. I'm done with my part.
Okay.
Okay, thank you.
Manu sir, please, if you have any questions, you can raise. Manu sir, please. Can you hear me?
He has some network issue. He has sent a message.
Okay. Mike is having some issue. Anand Singh, please.
Professor, this is an interesting talk. I have two doubts. First one is OH radical is very good for the oxidation of pollutants from wastewater. But how to use the OH radical for selective pollutants? For example, if I want to oxidize ammonical nitrogen, especially ammonical nitrogen, the wastewater is free of other compounds, to nitrate, the effect is very minimal. Whereas if I want to reduce nitrate to N2, there are people who have used carbon as a source to enhance the oxidation or the reduction. What's your suggestion on the first thing?
Yes, so actually OH radical is not always the main solution for depolluting water, of course. And so when you can reduce the compound for nitrate, there are a lot of studies about electro reduction of nitrate, for example. So you reduce nitrate it can be easily reduced, okay, and so that's interesting for that. So the reduction in this case is better than oxidizing, especially when the compound has a already high oxidation state. So in this case, hydroxyl radicals is not always more efficient, okay, than a reducing agent. And so in this case, I would prefer to use a reducing agent.
Okay. One more question.
Yes.
You have mentioned high reactivity with respect to the bicarbonate, sulfate, and chloride.
Yes.
Whereas we are dealing with the wastewater where the TDS concentration is 30,000, 40,000, where the carbonate, sulfate concentration and the chloride concentration is very, very high. It is not only single compound, it is combined. What will be the effect of combined compound on the OH radical generation?
So you will have a lot of competition. So yes, with water containing all these compound with high concentration, it can minimize the efficiency of advanced oxidation processes in this case. Then yeah, it depends. If you have, for example, a lot of carbonate or bicarbonate, if you could reduce the pH and then you remove the carbonate and bicarbonate. And then if you have chlorine and sulfate, it depends, but if you have double effect, you can have negative effects, but you have also positive effect by producing some other oxidants, chlorinated oxidants, that can also degrade the pollution. But in the meantime, you will also produce organohalogenated compounds, byproducts, and these are toxic, and you need to avoid that or to remove them if you produce them, or to apply a longer treatment time to avoid their production. And with sulfate also is the same. OH radical is reacting with sulfate to produce persulfate. And in this case, persulfate is also an oxidant that can react with organic compounds. And you can also remove, that can contribute to the degradation. But again, yes, then you can have also, it's still less reactive than hydroxyl radical persulfate, but it can still contribute a bit. The main problem would be if you have carbonate and bicarbonate, and then it's maybe better to try to remove them if you can, or use another process.
Okay, one more add-on question.
Sorry.
Please proceed. Please proceed.
So what is the impact of chlorine? Especially I'm talking about the chlorine concentration, as you have done the OH radical examination with respect to chloride, sorry, not chlorine, chloride. What is the effect of chloride concentration on the OH radical?
What's the chloride concentration with OH radical? So it depends as a proportion, you mean? It depends the amount of OH radicals, and it will depend on many things, and the concentration, the initial concentration of chloride. But what I can say for electrochemical advanced oxidation processes, which I applied more, is that it depends the conditions, the current density you apply. But at low current density, you could limit the production of chlorate and perchlorate, because you can control the amounts of OH radicals, which is easier in this case with electrochemical processes. Yes, but you can also have, so you can stop before chlorate. You can also have production of HOCl, so hypochlorous ions, that can also be efficient for disinfection. So in this case, it has been used a lot in for electro disinfection, for example, by producing HOCl with chlorine compound initially, and using also hydroxyl radical to produce these.
Thank you, Professor.
Dr. Emmanuel, I have 2 questions.
Okay.
So generally, methanol, ethanol, and butanol, etc., is well known for radical scavengers, especially
Yes.
hydroxyl radical scavengers.
Yes.
Even there are few articles which explain about the degradation of these compounds using hydroxyl radicals. Even one of your slides, it is mentioned that, I think that is for chemosphere article, you mentioned that for CCl4 degradation, first they used methanol for as an intermediate for generating
Yes.
radicals. So
Yes.
can you comment on this one?
Comment on the reactivity of methanol with hydroxyl radicals, right?
Right.
Yeah. So this was a work for other people. They were arguing that they could produce CH3 radicals from methanol reaction with hydroxyl radicals. I mean, I think there is still possibility of reactivity of hydroxyl radicals with methanol. Yes, sure, there's still possibility, because there are some hydrogen atoms, and there could be hydrogen abstraction. So I think it's possible for that.
Okay.
Yeah, and with terbutyl alcohol and other stuff, but the reactivity is much less than with other compounds that involve hydroxylation mechanism with unsaturated compounds.
Okay. So my next question is, you proposed in 2018 CCl4 degradation by hydroxyl radicals by a new method or a new mechanism. It's known as ipso substitution. What kind of compounds it is largely can come across these type of mechanisms. That means target compounds.
Target compound
Yeah.
in the studies was CCl4.
Instead of CCl4. Apart from CCl4.
Apart from CCl4, we didn't try other one.
Okay.
We tried CCl4 only.
Right. What about the carboxylic acids, oxalic acid, other carboxylic acid, whether it is applicable for this substitution reaction for the carboxylic acid or general?
If there are some halogen on it, you mean? If it comes for organohalogenated compound, it could be possible, as I said, with, for example, PFOS, for example, with perfluorooctanoic acid. There is a possibility. I think that could be one of the mechanisms responsible for its degradation.
Right.
Because there are many kind of bonds that we can have with perhalogeno-carbon compounds.
Right, right. Okay, thank you, Professor. Thank you for.
I have a couple of questions, Dr.
Okay.
Manu here. Yeah.
Yeah.
Okay.
Proceed.
Yeah, the rate of reactions which were shown on one of your slides, 20 or somewhere, where your linden and other compounds, rate of reactions, whether they are standard or whether they are for that particular condition, because it could vary. The rate of reactions could vary depending upon the reagents and then the temperature and other things. Yes. But yeah.
It's absolute rate constant. Normally, the absolute rate constant, second order rate constant, they don't depend on the condition. Okay. So the first order, yes, but not second order reaction. So to determine, I didn't show that, but to determine this kind of constant, you can use competitive methods with well-known compounds for which you know where the second rate constant, and then you introduce your compounds that you want to determine your second rate constant, and with competitive method you can get the absolute rate constant of your target compound, yes, by some formula. Okay, and so basically normally this constant doesn't depend on the conditions, applied conditions. But I was showing that it depends also the form, if it's acid or basic condition, because in acid, or if it's an acido-basic couple, then it's protonated or not protonated. And as I show with protonated compound, it's faster. So you could have a different rate constant in basic condition compared to acid condition. Because of that, if it's an acido-basic coupled compound.
Any specific reasons why the rate constants are more for these cyclic compounds than the alcohols and the straight chain compounds?
The reactivity is even higher with hydroxylation mechanism with unsaturated bond compared to hydrogen abstraction.
Okay. Thank you.
Yes.
Okay, thank you, Dr. Emmanuel, for this wonderful talk. Because till 2018, we have only 3 mechanisms of hydroxyl radical reactivity, that is dehydrogenation, dehalogenation, and redox reactions. In 2018, you clear that there will be another type of mechanism, that is ipso substitution reaction, that is only applicable for aliphatic compounds like CCl4. Even at that time, Professor Oturan had shared all the documents, how to all the reactions. At that time, of course, I didn't get most of the details. Now I understood the substitution reactions, how it's happening between CCl4 and hydroxyl radicals. The talk is very nice, and I think most of the viewers, especially the students and scholars, they may get some knowledge on these substitution reactions. Thank you for this wonderful talk, Professor Mousset. Now I would express my thanks to our panel experts, Dr. Manu from NIT Surathkal and Dr. Ambika from IIT Hyderabad and Dr. Anand Singh from NIT Calicut. Thank you for joining us and for this making this meeting very much interesting. Thank you all the
very
viewers.
much to you too. Yeah.
Thank you all for joining this meeting, and thank you all for the viewers for watching the program. Those who are unable to watch the previous programs, they can watch our Facebook account as well as our YouTube account for the previous lectures. So tomorrow at 5 o'clock, Dr. Parag Gogate will join with us with another new topic. It's on hydrodynamic cavitations. Who is the main expert in this field, Parag Gogate and Ebi Pandit. They will. So tomorrow, Parag Gogate will join with us regarding this hydrodynamic cavitations. Thank you for all watching this program. Thank you. Thank you very much.
Thank you.
Thank you. Thank you very much.